Hello, everybody. Welcome. I really appreciate you joining us tonight. I hope you brought your favorite beverage. We're sort of hanging out this is sort of a teacher hangout, and it's part of our series about the science and stories behind the NGSS. And I am honored today to be joined by Ned Gardiner from NOAA, who is one of those amazing artistic and scientific talents behind a lot of the beautiful maps and imagery that you see coming out of NOAA around climate and weather issues. And this is sort of an interactive conversation. The Q&A session is open, so please feel free to write questions at any time. We're going to entertain them and talk about them, and if you have things to share, there will be an educational resource component to the Hangout after Ned gets a chance to talk about some of the science and stories. And tonight is all about the winter weather outlook, which was recently released earlier in October. And it sparked in me the question of, I don't remember seeing winter weather outlooks. I mean, obviously we're very used to weather forecasts, but like seasonal outlooks seem to be something that I don't really remember until recently hearing about. So that's when I thought this is a good opportunity to talk about climate modeling and seasonal modeling, and then how we bring these into the classrooms. So with that, I'm going to introduce you to Ned. I'm going to switch over and say hello, Ned, if you'd like to introduce yourself and talk a little bit about where you came from in terms of, I know we've gotten to work together in the past. It's great to get to work with you again tonight.
And thanks for the invitation, Rachel. Hello, everyone. I can't see your faces in the Hangout, and so I guess since this is a small classroom setting, I would ask that you feel free to raise your hand and bring questions forward at any time. I'm eager to be participating with Rachel and WGBH as an active viewer of the programming. It's really fun to be able to be part of something new in this forum. So I'm going to jump over to a set of slides to introduce myself a bit more, and if you'll bear with me, I believe you can see my screen now, and I will be talking about the winter outlook for December, January, and February of this year and next calendar year, which is what meteorologists define as winter. Oddly, you know, and I'm not sure why this is, they don't time it with the solstices and the equinoxes, but they use the even month designations. And so you'll notice, since it's December, January, February, when we issued this outlook on October 16th, we're actually a month and a half away from the beginning of that 90-day period. So as I go through this presentation, keep in mind that the technology and the expertise that have been developed to provide climate forecasts is very different and distinct in some ways from weather forecasting. It is definitely beyond the scope of weather forecasting, and I'll come back to that in a moment, but I do want to tell you a little about myself, because I came into this communications and education field through the back door. I don't have formal training as a teacher, and I don't have formal training in pedagogy. My background is in geographic information systems and remote sensing, actually watershed modeling to study macroinvertebrates, algae, and fishes and streams. And I got involved in visualization as a way to promote a broader understanding of the Earth system and ecosystems. Essentially, I'm an ecologist who doesn't want to study ecosystems literally to death. I want to be part of a generation of people who are understanding systems and using that understanding to make better decisions. And I got my start working side by side with Rachel at the American Museum of Natural History, where I was the science advisor for 2 content streams with the Science Bulletins program, and I think that Rachel has a link to Science Bulletins in the resources we're going to give you at the end of this seminar. The 2 content streams dealt with Earth systems, which you see visualized on the left side of your screen just two examples of data visualizations that I helped produce on sea surface temperature and sea ice, but we produced dozens of them. And on the right, biodiversity, using satellite remote sensing, climate models, and modeling to understand changes in biodiversity patterns around the planet as a result of human decisions. And really the philosophy of the program was to show people what we can see with our own eyes in real time about how humans are changing the planet, which to me is the theme of our generation, to begin to embrace and understand the ways we're impacting and influencing the distribution of life and indeed the processes that govern the Earth system writ large. I've moved over to join NOAA's Climate.gov web team. I've been integral in the planning and the design and the implementation of the site, which includes 4 sections: a news and features section, a map and data section, a teaching climate section, which is really oriented to folks like you, and a supporting decisions section, which is for decision makers. On the right, I've just pulled a few examples of videos that my team has made about which are designed to show people in terms they can relate to the consequences of climate factors. So we see recreation on a river here in Florida and the supply of water and how that relates to climate variability. A tool in the middle panel on the right, the Weather and Climate Toolkit, that's designed to help data users access and use NOAA's data. And on the bottom right, it's a screen grab of the winter outlook, which we're going to dive into a bit more.
Ned, I don't want to interrupt. I just want to let everybody know that every link to every site that we're going to speak to tonight is already in the showcase, which is available to you on the event page. And I'll be showing you where to find those at the end. So you don't have to feel like you have to keep taking note about where the sites are. Okay? So, sorry, Ned.
Not at all. Please feel free to jump in at any time. And hopefully you can hear me well. I'm actually lowering my voice just a little bit to pace myself. So this is the thumbnail image off of our video that we made about the winter outlook. We made this in about a 36-hour period, right leading up to the release of the outlook on October 16th. And we chose this image because when most people think about winter, of course, they're thinking about snowstorms or extreme warmer than usual or colder than usual temperatures. So what the outlook does do is give you a sense of, on average, should I expect the season to be wetter or drier or warmer or colder? It does not speak to extreme snowfall or persistent blocking patterns in the atmosphere. Atmospheric phenomena that lead to weather conditions like a snowstorm are not predictable beyond 2 weeks at all, and generally are stem from transitory conditions in the atmosphere. What the outlook does is look at the state of the ocean and general behavior of the climate system based on trends and observations to give a sense of whether on a national basis we should expect different average conditions. So hopefully all of you understand that distinction between weather and climate. But before I go on, please raise your hand immediately if that distinction is not clear.
We do have a question. Kurt just asked a question. I think you addressed some of this already, but let me ask the entire question. Kurt asked, how are climate forecasts different and similar to a weather forecast, and how reliable are they, and who uses them?
Okay, well, really, my whole talk is about that. So, I'm gonna get into how they're different in just if you'll hold on to that idea. That's really the subject of the next about 25 minutes. And who uses them is primarily these outlooks go out to the weather forecast offices throughout the country as well as directly to the media. But what I'm learning is that these go to the people in your local or regional weather forecast office, and they're able to give you more context in your area about whether you should expect conditions to worsen or improve, say, and so I'm going to get into that a bit more as well with respect to California. Because right now, in the nation as a whole, interest in the outlook is greatest out here, out west in California, where climate conditions have led to a very serious drought in one of the world's most productive agricultural regions, California. Kurt, I believe, is the Kurt I work with, making films such as this one that help people understand the impacts and the importance of the drought out west. You just saw some examples of kinds of impacts in ranching and in water supply and reservoirs throughout the state of California. And by focusing on this region, I don't mean to exclude anyone in your geography, but it's a good example of how this outlook can be used and applied to a specific problem. Because the state forecasters in California want to know and want to help their constituency better understand whether they're going to be able to come out of this long-term drought. Let me explain this graphic a little bit that you're looking at. The map on the left of California has 4 shades of color on it that represent moderate, severe, extreme, and exceptional drought, going from the lighter orange through the dark red. And the dark red, D4, is a drought that you would not expect to see more frequently than every 50 years. And indeed, California is in the midst of that most severe category across almost 60% of the state right now. And if you look at the table on the right and look at the current conditions at the top row and the upper right corner, that D4, 58.4% of the state, and then scan down 3 more lines to the start of the calendar year, you can see that a year ago, almost a year ago, none of the state was in that drought. But the conditions that set up the drought started, in fact, 3 years ago. So the climate system sets in motion processes that can accumulate over time and can take a long time to be felt. On the flip side, people looking at the outlook who want information from this want to know, are we likely to reverse that trend over the next season? So what does the outlook say? Does the outlook suggest, for instance, California should feel optimistic about reversing that trend? This is the precipitation outlook for the nation, for the lower 48 states. And I've just zoomed in for convenience so that you can see clearly. And I've given you sort of an easy to interpret version of the map. Everything in white on this map, not gray, which the oceans and the continent in general, like Canada and Mexico, are gray. The ocean is a gray. But the white color over 2/3 of the country, roughly, is an area with equal chances for above, near, or below average precipitation, which means essentially that climate science does not provide any tilt in the odds away from normal conditions over the December, January, February time period. Could it be a lot drier than normal in Nebraska? Yes. Could it be a lot wetter? Yes. Could it be near normal? Yes. Now the concentric circles in the Pacific Northwest or around Lake Michigan there The first ring, that first line of the first ring, is actually a 33% probability line, which means that there's about a third chance in that first ring that you'll have a drier than normal, or to put it more precisely, that the winter will be in the upper third of observed winters for dry conditions. Okay, so these are probability maps. So for those of you who are teachers, helping your students understand the notion of probability is essential for reading and understanding these maps. The next ring in, that's darker brown, that's a 40% contour line, meaning the probability is greater that it will be in the upper third of dryness, or in the 33% of driest winters. I'm going to finish my explanation. I want to make sure everyone understands that idea before I go on further.
If you have any questions, please feel free to ask them in the Q&A section of the chat box, just so everybody knows.
So, and similarly, the aqua color at the bottom, the lighter shade, that's a 33 to 40% interval in the first band and a 40% and above in the lower band. That is the likelihood or probability that we'll have a wetter than normal season in the southern tier of the United States and extending from the southern part of California up along the East Coast.
So, Ned, can I ask a question? And this is sort of around the word usual and how usual is being used here. Right now, half or a little more than half of California is white. So if that means it's going to be about usual, does usual mean the drought it's experiencing now? Or is usual sort of a broader normal that,
That's a great question. So embedded in that, I heard two important ideas. First of all, the white area does not indicate an elevated chance of near normal. The white indicates that there's no tilt in the odds one way or another.
Okay.
So for the white areas, there's about a 33% chance it could be drier than normal, 33% chance it could be near normal, and a 33% chance it could be wetter than normal. So if you think about a bell-shaped curve representing the probability of the whole observed record of precipitation, the bell curve for that white area directly overlaps all the observations.
So is California happy with this map? If you were talking, if you could speak for them, do you think that they're happier with it or not?
This gets back to Kurt's question as well. Who uses this information? The Western Region Climate Service Director for NOAA's Weather Service is based in Salt Lake City, and her responsibility is to help people like in the weather forecast offices throughout California, in the wine producing areas, in the agricultural regions, help them understand, are we going to come out of this drought? And fact is, there's a 2 in 3 chance that they could have a near normal or above normal season this winter. But that's probably not going to be enough to come out of this drought.
Okay. So,
no, people in California are potentially in the midst of a longer-term problem. And that's, we saw a persistent drought episode in the earlier part of this decade through Texas and Oklahoma and the southern plains. And the cattle industry is still recovering from that. So these droughts, these persistent droughts, introduce real hardship for people. And preparing for that is very important. So emergency managers need to know, am I going to have water for fighting fires? Am I going to be able to, what provisions do I need to put in place to deal with the aridity in the landscape?
Is anybody in our audience, I guess I would like to just ask if anyone in our audience happens to be from California or in a region maybe that's experiencing drought that isn't California. So please share in the Q&A section. We'd love to hear from you. So, Ned, please go on.
Okay, my computer's hung right now, but there we go. Excuse me. This is the outlook for temperature, which indicates some elevated probabilities for a warmer than normal season for December, January, February for much of California, for Oregon and Washington, and a narrow slice of Nevada, including Reno. That band is actually at a 50% elevated chance. So what I'm saying is there's a 50% chance that that region of California, that band, is going to experience a warmer than average winter. And as we move westward, we see that probability decreasing. So imagine in your mind, you're all science teachers, or you're all in the communication of this information. Imagine that bell-shaped curve for all the observations, and imagine another curve representing the probability distribution of the prediction, and imagine that that prediction shifting from the right, which is the warmer, toward the center as we go from west to east, and then it's kind of overlapping all the observations over that white area, and as we move, that bell-shaped curve of the prediction moves even further to the left towards cooler as we move into the southern tier of the United States down towards the Gulf of Mexico in that band of 30 to 40% likelihood of a cooler than normal winter. If you would like more of an explanation of these concepts, Kurt and I have developed some videos that really explain this really well. And we're going to make sure you have access to those in the resources section. I'm going to go back over that with Rachel and make sure you've got those, because I've got visualizations of those curves and everything. Raise your hand right now if you'd like to see it now, and we'll go through it.
I think we're good to go on in the short term.
Okay, so I just strongly recommend you take and use those. They're excellent for the classroom, and they really open up some possibilities for doing exercises with data. So how do forecasters make these climate predictions on a seasonal basis? I believe that was part of Kurt's question as well. I'd encourage you to dive deep into this question, one aspect of this question, by visiting Climate.gov's ENSO blog. Because the very first, and I've given a link to Rachel, she's included it in your resources, the most powerful predictor for seasonal conditions in the United States during winter is the state of the El Niño Southern Oscillation when there is a strong event, such as El Niño or La Niña. So raise your hand right now if you don't know what those terms mean at all, and let me know, Rachel.
Sure. So just to clarify, ENSO, and I didn't know this even until we started preparing for this hangout, stands for El Niño Southern Oscillation.
Right, and I'll just give a general introduction and review for people if they are somewhat familiar with this concept. The El Niño La Niña Southern Oscillation ENSO stands for the El Niño La Niña Southern Oscillation, which is an oscillating pattern of warmer and cooler temperature in what's called in the Central Pacific Ocean, which I've highlighted in the upper right-hand corner of this slide. The Niño 3.4 region is where NOAA monitors ocean temperature to define these states. So we have to be in over 5 consecutive 3-month periods that are overlapping. We have to see a 0.5 degree centigrade increase in average ocean temperature over the climatological average to define an El Niño, and a 0.5 degree below average temperature for that same length of time to define a La Niña. Now, what causes it is much more interesting than just a statistical property. What's happening in a La Nina is the predominant wind pattern, the easterlies, are pushing water towards Indonesia, and you get upwelling, and the currents from the deeper ocean bring colder water to the surface that make the average temperature at the surface colder than normal. And this is accompanied by changes in atmospheric pressure and changes in the dominant precipitation over the Pacific Ocean. What do you think happens when you have colder ocean water to precipitation in the central Pacific? If you have colder water, you have less evaporation and less convection and less of an atmospheric disturbance. Instead, there's more. There tends to be more rainfall over towards Indonesia, over in Oceania, and that greater disturbance to the west in the Pacific Basin affects the jet stream further to the west and sets up a whole series of teleconnections. Kurt and I have also made an excellent video that explains that. And during El Nino, the situation's somewhat different. A Kelvin wave, which is a vertical mixing of the ocean from Indonesia toward the Americas, brings a pool of warm water at depth further to the east that then surfaces, and we get a warm water emerging at the surface, and we get something called El Nino. During El Nino, we get more evaporation and more rainfall activity in the central Pacific, and that affects the jet position high in the atmosphere that then influences conditions in North America. For example, by increasing the extended jet across the southern tier of the United States, we get wetter conditions generally. And people in California really remember the 97-98 El Nino because it brought a very wet winter. What's been happening in California over the last 3 winters, this winter, over the last the two previous winters, was there was a high pressure ridge blocking weather conditions, blocking the emergence of rainfall across the entire state. That has nothing to do with El Nino or La Nina, and it has more to do with climate variability in the Pacific Ocean. And so you can see there are different long-term processes that come into play in the Earth system that create these patterns that are very important to us, to our predilection for wine, for instance. California is a Mediterranean climate, so it gets 2/3 of its rainfall during the winter, and typically is dry during the summer, and that's what makes an excellent wine. It's also makes for an amazingly productive agricultural region when you can irrigate the soil, when you can bring in water, and that's what we've done. Our entire development of the western United States centers around irrigation canals, diverting water from as far away as the Colorado River Basin all the way into the Central Valley of California. And what's a concern now is water supply through irrigated channels and reservoirs, not only for agriculture, but for municipalities, for fisheries, for emergency response, and the natural supply and replenishment of precipitation during winter for crops such as grapes that really need this supply to be replenished during winter. So El Nino, as I said, is the most powerful predictor for winter conditions in the United States when we're in a strong El Nino event. The next tool that climate forecasters use when they make their seasonal forecasts is the observational record. They use the observational record to assess, are there trends? Are there characteristics at play today that give us clues based on the historical record of what we should expect? And to be blunt, these statistical techniques are too complex, I think, to address at a high school level. They're multivariate statistics. They bring in and they blend data from stations and gridded data. But I do think there's a tremendous need for climate literacy and for statistical literacy and the ability to read maps and use data and understand and blend different sources of data. Because when you sit in on a climate forecasting session, you can see that the scientists doing this work are processing information from all these different sources and having to weigh and evaluate the strength and importance of these different sources of information. So what I've done for tonight is pulled out and provided an example of data that you can pull down and analyze for yourself and work with your students. I'm giving you a link at the bottom here to generate the graph we're looking at using the National Climatic Data Center Climate at a Glance tool. The National Climatic Data Center is the world's largest repository of climate information, and it's here in Asheville, North Carolina, where I live. And the climate monitoring branch of NCDC has put together this really clever tool that I think is very well suited for use in the classroom. What you're looking at in this graph is the December, January, February rainfall record with a gray line through the average rainfall, or not rainfall, precipitation, including snowfall, snow water equivalent. This gray line represents the average for the 20th century, and what you can see is year to year or over a period of 5 or 10 years, you get tremendous variability. That's the norm in the climate record for California, is incredible variability. What's unusual about the last 3 years is that 2 of those years were among the 5 driest years in the entire record, going back to 1895. And so that, when I spoke before about the momentum in the climate system, that this has been building over a number of years. A year ago, California was not in a severe drought, but it was heading there, and we knew it. And Kurt and I were reporting on it. We were telling you through our broadcasts that the snowpack is not sufficient to replenish these reservoirs, and we were working with Deke Arndt of the Climate Monitoring Branch, who was saying, you know, over time, it's this persistent lack of replenishing reservoirs that leads to a problem. And now if you, I think Kurt interviewed Deke a few weeks ago, and Deke said this is the climate crisis in the world right now, is California. So get your students to look at these data and start relating those data points on this graph to really a deep and important climate event. I'm refraining from saying crisis deliberately, but for many people it is. This is a hardship.
So Ned, yeah, I was going to say this. I want to just quickly say that Joseph asked a question about the jet stream. When you have an opportunity to talk about the jet stream, we should go back to it, so I don't want him to think we aren't ready for that. Okay, so Joseph asks, he understands the polar jet stream, and he'd not heard anyone refer to another jet stream closer to the tropics. Is there a jet stream at the meeting places of all atmospheric circulation cells?
That's fantastic. Great question. The polar jet is a loosely defined region that circles the Arctic and that meanders in response, and it's essentially it's loosely defined as the place between the high pressure in the Arctic and the lower pressure at lower latitudes. And it's really not well defined mathematically, but the point is, at that boundary, you get an increase in you get a high level atmospheric circulation that moves. Jets occur in mid latitudes as well. Anywhere where you have a gradient between a high and a low pressure. And so essentially what I'm saying is the El Nino generates one of those gradients that amplifies or extends this jet, a jet in the mid-latitudes. So you can go to the American Museum of Natural History where we set up a climate observatory of sorts where we've labeled a number of mid-latitude jets over time, and you can see how they interact to form storm systems, and you get spinning off mid-latitude cyclones coming off of those jets.
So are there, at any time, are there different numbers of jets on the planet, or is there sort of a set number of jet streams that, you know, that get stronger and weaker, that are persistent?
No, it's not a set number, and it's a heuristic. It's a description of the emergence of wind patterns between zones of high and low pressure.
Okay. Got it. Well, thank you. Good question, Joseph. I appreciate it. So we're going to move on. And I want to return to this tool because I had not seen it until Ned was preparing this hangout with me, and I think that some of the access to data, and I mean broadly data, astronomical, Earth, you name it, but particularly climate data, can sometimes be intimidating to non-scientists. But this is one interface that I did find to be particularly user-friendly and quick to generate some graphs. And what you see there, what Ned just showed you, was that graph.
I'll come back to it in just a second. I wanted to remind people that we're still talking about how to generate these outlooks. And so statistical techniques using the observational record are essential for climate science. So just to reinforce where you're going, Rachel, we want students to interact with data and plot data.
Right.
They are actually building a skill set that can be used in applied climate science. So this is a good place to start because it's simple.
Yeah. If you want to get into some of the data around precipitation, I mean, the parameters here, there's a nice drop-down menu. You could select from multiple parameters.
Yeah, let me take people through that, in fact.
Right.
We're looking at the interface. Just I'm deliberately not doing a live demonstration from the website because
it's down.
The entire building, the power supply, the whole building. This is just a freak circumstance. The power supply is being completely replaced tonight. So I don't want to risk doing any demonstrations on the live website, but the link is available in your Hangout.
Yes, in our collection of resources we put together for you. You will find the link to this.
So notice that there's a place to drop down and pull down the parameter precipitation. I've chosen a 3-month period ending in February for the entire period of record from 1895 to 2014, and we're looking at California, a statewide evaluation of precipitation. And so here, I'm going to play a little movie of me interacting with the website. But we're starting here by looking at the climate normals. Annually, we expect to see 31 inches, and in winter we see 18 inches. That's almost 20. That's almost 2/3 of the rainfall comes during winter. So you can see it's completely essential that during a drought you would want to see your precipitation replenished during that period if you want the annual average to come up. So here, through this interface, I'm about to choose precipitation in the parameter space at the top. I think because I recorded this film while I was doing this Google Hangouts earlier today, the internet latency is slower than average, so just please be patient. I'm choosing a 3-month period. I'm going to choose the precipitation parameter here in just a second. Coming, there we go. Okay, so it's actually fairly intuitive how you do this. You choose the month that you want to end your analysis, and then I've chosen the whole state of California, and then I'm going to plot the data by clicking the blue plot button, and I'm going to scroll down, and you're going to see this map, now this graph, and that graph is interactive. You can zoom in and out of it. It's using a technology called multigraph that was developed here at the University of North Carolina in Asheville that allows you to interact more with the data. And below, at the bottom of the page, you can see every year's data. So this is the information that our climate understanding is built on. And if you can get your students working with it, you're giving them real skills that they can take into their scientific career. So I'm inviting you to dive deeper with your students into the Climate at a Glance tool. You don't have to look at California. You can look at your own region. You can look at the nation as a whole. You could also look at the Integrated Surface Database to go straight into the values and the climate normals for every station in the United States. If there are any questions about any of that, I'd be happy to take them now or offline. But I just wanted to give you a sense of working with data because that's really what climate science is about. The third tool that forecasters use is climate models. So I think we all have an understanding of what a climate model is, but in climate science, there are different kinds of models for different applications. If you think about the kinds of models that weather forecasters use, they're different from the kinds of models that scientists use when they do climate projections for the IPCC, looking out a century or over decades and decades. The difference between these models is beginning to break down because some of the techniques are being applied in both domains. But traditionally and historically, the difference has been that to do a seasonal forecast, you look at the current state of the ocean and you seed that as a boundary value condition to start the model, and then you let it run for 3 months or maybe a year to look at what evolves in the climate system. Now, different models have different ways of representing the physical processes that would play out. I should say, just for balance, that the climate modeling that's used for a century scale look at changing the boundary conditions of greenhouse gases and solar radiation and sulfur dioxide from volcanoes and all of the different factors that can influence heat in the atmosphere, whereas the climate models used in seasonal forecasting look really at the initial conditions of the state of the ocean and how those affect nearer term processes. So the different models really address different questions.
So Ned, I know the complexity of these models, and I do want to just sort of say that, you know, for educators, modeling and using models is an increasingly important part of, you know, our standards and curriculum, because models are becoming, with the computer power and processing power behind them, are becoming so much more a critical component of how this research is done, or how research in many fields is done. But the complexity of them sometimes is staggering to me, around how many variables and parameters go into a model. So, for example, Ned, I mean, this was amazing right here, the image you're showing, because you get to see how many different models get used.
Right. So what you're looking at here is a panel. This is a panel that climate forecasters would actually consult while building their forecast. After they look at ENSO, after they look at observations and statistics, they begin looking at what do the models tend to say. And they would look for, now remember, each model, if you look at the bottom half of the page, there's 8 squares with maps of the United States indicating surface temperature as predicted by 8 different models. So that's essentially 8 independent realizations from 8 independent modeling groups around the world, giving a sense of what could happen in North America in response to the initial values of sea surface temperature in the ocean system. And they don't all say the same thing. So what forecasters look for is there broad agreement? Is there support for my forecast? If there's not agreement, what might be driving that? What processes do these models tell me about that I haven't considered? And it's a young science. These forecasters are learning all the time from the models, and they're continuing to bring their own expertise to bear on whether or not the model information is trustworthy. At the top panel, we see NMME, the National Multi-Model Ensemble. This represents essentially a whole suite of models, and what do they collectively say about the potential temperature patterns in the United States over a seasonal basis. And the IMME in the upper right is an international multi-model ensemble. So I've shown you this. In the center, you're looking at a probabilistic forecast, which incorporates some statistics about agreement and so forth. The reason I'm showing this is to indicate the kind of the diversity of things that computer simulations can provide to a forecaster as they evaluate what is what might be coming in the upcoming season.
So, Ned, when we see the winter weather forecast and it's one map, essentially, is that all 8 of the ones below sort of averaged together? Is it some people, some experts who look at all of these and then generate that one from, you know, they're being informed by this and what they know? Like, how do we get from all this to one?
Let me review again where we are in. Remember I told you there are 4 tools that forecasters use. And my computer's going a little bit slowly.
So
there's the state of ENSO. That's the first tool.
Okay.
The second tool is observations, and we talked about statistics using a simplified example. The third thing is models.
Uh-huh.
This is, and it is hierarchical. This is less important than the state of ENSO and less important than the observational record and the observations. But it is an unimportant piece of information. So there are people who think we should be, and that we are moving in the direction of just having computers generate a forecast. But that is not what happens with the seasonal outlook. I'm about to describe that in a little more detail, but we have, let me just wrap up this modeling section, because in a sense you're just one step ahead of me. Climate models do provide a dynamic representation of how Earth's processes can evolve. Where these models have proven to be very effective, it can take months and months to analyze and understand what the models are telling. But remember, these forecasters are using model information every month. So they're rapidly learning from the research community and applying new information and coming up with new ways of using this output. So we really need young scientists, your students, to be getting involved in this discipline of modeling. So this is the answer to your question, Rachel. The fourth and final stage of developing a forecast is a diagnostic discussion. And here you see Mike Halpert drawing on a map. This guy has been doing climate forecasting for 30 years, and he wrote a seminal paper on the role of ENSO in diagnosing potential precipitation patterns in California. So it's really the combined expertise of people like Mike and his colleague John here, looking at the data and analyzing the data and evaluating how much importance to place on different sources of information. Here they're participating in a conference call that's national, where they bring in weather forecast offices and climate experts from different regions around the world, and they're evaluating the outlook that they generated last spring. And this process is very much one of the process of science. It's very much about the expertise and the accumulated wisdom of people who have developed an understanding of the data. So that diagnostic discussion is critical in generating the final output. So I really want to leave you with the strong sense that this California drought, it's the largest climate event on the planet right now, and it's following major droughts that happened in the southern plains earlier in the decade. So there's intense interest in this year's winter outlook. It doesn't seem that California is going to get major relief, and we do need your students engaged in this activity of climate forecasting, so that, answering Kurt's question, there is more information on the ground where it's needed, so people can prepare for potential water shortages or other climate-driven events. So with that, Rachel, I think I should pass back to you so you could go over the...
There's a lot. I think there's a lot to process on the science side. I would really love to see if anyone has any questions at this point before we talk a little bit about some educational resources and that teachers might use to bring some of this content into their classroom, which is what we sort of have for you. We've put together a nice suite of educational materials from NOVA, PBS, NOAA, that we want to walk you through a few of and point you to. But if anyone has any questions, now's the time to ask them before I jump into some of the educational resources. So I'm going to move on and share some of the things we have queued up for you. If you have some things along the way that you as a teacher have found particularly useful in teaching some of these concepts, I ask that you go ahead and share them. It'd be really nice to hear from you about what you think has worked really well. And if you have some topics that you're teaching in the classroom that you don't quite know how to connect maybe to some of this, or if you'd like to ask if we have any, if you need any help, now's another really good time to ask that. So we invite your input, and I'm going to go ahead and jump over and share with you. First and foremost, I like to start with where the standards are on some of these topics. And I pulled both of these two that we have here on the screen right out of the Next Generation Science Standards, because I think that while the story here to me at the beginning of this is models, and where modeling and what modeling has to play a role in this real world, you know, climate modeling piece of things, it's also about how it plays into natural hazards and being prepared, like Ned said about California, being prepared for some of these inevitabilities. And I unscreen shared, so I apologize. That's my fault. The other story here is about how climate models enable us to talk about global, regional climate change and future impact. So part of this is about, you know, our everyday lives, and we have a fair number of wonderful resources for teaching some of these topics. and I want to point you to just a few of them. Ones that we have to share are on PBS LearningMedia and Climate.gov. So we're going to start there in both places and sort of walk you to a few specific things. Again, all of these links to the specific items have been collected for you, and I will share that link at the end. It is in the showcase that goes with this event, so you can browse at any time you want to explore them. So PBS LearningMedia is the educational platform and digital library for all of the public media resources, and even beyond public media only, but partners such as NASA and NOAA also have a lot of resources on PBS LearningMedia. 87,000 digital tools for educators exist on this site, and one of our marquee science brands that has their resources here is NOVA. There is a particularly wonderful collection called the Earth System Science Collection that was funded and supported generously by NASA's Earth science efforts, and that is also who's enabled this hangout today, so I just want to thank them for supporting all of this Earth science education work. But the collection here includes beautiful short videos that have been pulled out for their educational connections from a NOVA program called Earth from Space that some of you might have seen. It's a beautiful two-part special that if you haven't seen the whole thing, I would recommend it, given if you're interested in these topics of Earth science and climate. But what is great about it is that so many of the resources feature data visualizations and satellite imagery similar to some of the things that Ned has shown you tonight. And this is just one clip I took briefly here from the Global Ocean Circulation resource. And the support materials below have a lot to offer to help you integrate this video clip into your classroom or your curriculum. There are connections for you, background essay on the content of, in this case, the ocean currents and how they impact planet temperature, which is what this is connected to what Ned was talking about earlier. A for teachers section that helps you talk about like the main student ideas that you would hope to see from the learning that comes out of using this. Some discussion questions for you to use with your students, and some other teaching tips, and finally connected to the national education standards. So there's a whole collection of these available to you. And another one that I wanted to just call out is there's a La Nina one, although Ned spoke about El Nino. There's one about La Nina that also has some similar beautiful visualizations about some of the temperature differences that you can view from space, and makes these ocean sea surface temperature patterns very visible. The other resource I would like to share from NOVA is one of the NOVA Labs collection of sort of real-world scientific investigations that connects real data to some tools and videos that make it useful for teen audiences and classroom use. One lab is called the Cloud Lab, and in the Cloud Lab is an exploration of how you can track, in this case, Hurricane Sandy, and the story of how it evolved. But there's a section called Open Investigation that gives you a tool that I wanted to show you. This is real data, as in like right now, today, that has been gathered of what our cloud patterns look like from space. So the reason you have these little slices, and Ned, you're probably better positioned than me to even speak to why these slices are here, but these are because you have a band of observation coming from a satellite going around essentially a sphere, and those little slices are where the bands they miss.
These are the orbital tracks of MODIS, the Moderate Resolution Imaging Spectrometer from NASA, and so they generate an image of Earth twice a day, but each band represents a different time on the planet. And these have been composited into an image. It takes about 105 minutes for a satellite to orbit the planet. And so over the course of the day, those swaths are collected and formed together to give you that one mosaic image. And as you can see, there are gaps between the orbital tracks.
Thank you. Thank you so much. I didn't know that level of depth about it. But the reason this tool is useful is for a couple reasons. There are a couple overlays that you can select that are helpful when you're talking about weather and severe weather. So if you hear that there's a hurricane or a typhoon or something happening, this is a place to go and quickly connect to some of the satellite imagery and some of the overlays like precipitation, water vapor, cloud temperature, and there's also the ability to pick a few existing storms that have happened in the past and go to it and have an investigation question that sort of gives you a focused way to look at the data and investigate. In this case, where did the storm contain the heaviest precipitation rates? So it gives you some sort of guiding ways to start looking at real data with your students, because I think, as Ned said, this is increasingly going to become important for many fields, not just if you're going to be a scientist, but just to understand some of these data sets and how to explore them. And that's why these tools are useful to get students started early in the data and that. Now, moving on to some of the great resources from NOAA, Climate.gov has, when you go to it, a section called Teaching Climate that will connect you to a whole host of resources. I'm going to actually put, since today's, we talked about drought so much, I'm going to put drought in the search box and click Find Resources. If you are a teacher in a particular grade, you can pick what grade you'd like to look at. But this gives you 9 resources. There's a collection, there's multimedia resources, demonstrations, experiments, and PD. And it connects you to some really good, and I would say highly selective. And they've gone through the clean collection of resources, which I think includes approximately 600 right now, Ned. I think 611 have gone through 8 levels of review. So we're talking about some of the most, for accuracy and educational quality. This is one of them, connected to what Ned was speaking to tonight. This is investigating El Nino using real data. So if you want sort of a guided way to get into some of the data, this will help walk you through it and has a complete curriculum that you can download to help you. So another one that we'd like to call out is one called Normal Climate Patterns that gets into, there's one particular unit within that that focuses on drought, particularly in what a watershed is, droughts of the past. So it's a beautiful collection. All of the links to these resources have been compiled into a single folder, plus the notes about them. This folder, which does exist on PBS Learning Media but is absolutely accessible to everybody. PBS LM is free. Anybody can use it. You do not have to log in. It's just a way for us to capture all these in one place. That link to this exists in your showcase. So you'll see on the side of this event that you can enter your showcase and get to this collection and any of these other resources that we've talked about. So I'm going to unscreen share and see if anyone has any last questions or things they'd like to talk about before we wrap it up. And Ned, thank you so much for spending time with us. I learn something every time I talk to you, and I never get to talk to you quite frequently enough. So
you're very welcome. Thank you for the opportunity.
So I don't think we have any more questions coming in at the moment. So I think we gave people everything they probably needed and more about the winter weather outlook. So here in Boston, it looked like we were going to have cold, wet weather. So everything, that's all I need to know.
Let's do a little quiz. What did the outlook actually say though? Remember, it's probabilistic.
There was a probability, a 33% probability that it would be wetter than usual.
Okay, good. Just so you're up on that. So we're not saying what the weather's going to be, but the average conditions are leaning
Wetter than usual.
Wetter. There you go.
And that's only a 33% increase or a probability.
I think the one question I didn't answer from, I think Kurt posed it, was how powerful are these forecasts? And I should emphasize that since ENSO is the biggest driver of these forecasts, the likelihood of an ENSO event is down around 2/3 now. Earlier last spring, we were predicting a high probability of a strong El Nino event. That's not being predicted now. But these predictions overall give at least 25% to 30% improvement over just average climatology. That's not a strong amount, but if you're betting over time, if you're making investments in energy, if you're putting your money down, that extra margin is something you can take to the bank.
That's a good way to put it. And with that, thank you, Ned, for a wonderful evening. And everybody, I hope we see you again soon on the next Stories in Science behind the NGSS. Thank you again for your time. We'll talk to you soon. Bye.